Hi, let us continue with our discussions about the design of reinforced concrete peg footing subjected to axial loads together with the moment acting in the major axis. So far, we have done checking the shear resistance at the shear plane located at 1d distance from the column face. Also, we have done the checking in terms of the punching shear at the perimeter of 2d from the column face. These are two types of the shear that can fail a peg footing. There is one more shear that we need to check, which is the maximum punching shear at the column perimeter. We will need to check the shear resistance at the perimeter of the column in order to prevent the column from punching through the peg footing. In order to check the maximum punching shear, first we need to determine the shear force. The shear force can be determined from the ultimate axial loads from the column, which given in the questions equals to 1000 kN. Based on the ultimate shear loads, we will need to convert it into shear stress by dividing the ultimate shear loads with the effective shear area. This effective shear area is calculated based on the U0, which is the perimeter of the column face, and also the D, effective depth of the peg footing. The equations used for the punching shear at the column perimeter seems to be the same as the punching shear at 2D perimeter, except that the shear load that you use for the 2D and the shear loads that you use at the column perimeter, they are different. The shear load for the 2D perimeter is calculated on basis of the average soil pressure at the ultimate limit state, multiply the area of the peg footing outside the 2D perimeter. As for the shear load for the maximum punching shear, we will take it equals to the total axial loads acting onto the peg footing. Also, the effective shear area differs. For the punching shear at 2D perimeter, we are talking about this as the effective shear area, which is calculated based on the perimeter of 2D multiply the effective depth. As for the maximum punching shear, the perimeter, it will be the column perimeter multiply the effective depth. Other than that, we will need to take into considerations of the influence of the moment. This is represented by a factor of beta. The equations for the factor beta is similar, except that the perimeter and W1s differs. The perimeter for 2D is referring to this perimeter, whereas the perimeter for the maximum punching shear, it will be the column perimeter. And also the equations used to calculate W1, it will be different. Now, having this understood, let us look into the calculation steps. First, the VED, it will be the total ultimate axial loads acting onto the peg footing. In this case, we are talking about 1000 kN. And then you need the U0. U0, it will be the same as the column perimeter. We know the size of the column. The width is 300, and the other side in the minor axis, it will be 150. 2 times 300 plus 2 times 150. That will be the U0. And then we need to calculate the W1. W1 will depend on the C1 and C2, which we have calculated it earlier on when we talk about the punching shear at 2D perimeter. You may refer to this diagram for you to determine the C1 and C2, assuming the moment is bending in these directions. The width of the column parallel to the moment, it will be the C1, whereas the other side, it will be the C2. In this case, the moment is in the major axis. Therefore, you know that this it will be the C1, which is 300 in the major axis, whereas C2 it will be this side, which is 150. Substitute the value into the equations, you get W1. Now you have U0, you have W1. The moment is given, which is equals to 150 kilonewton meter in the major axis. The VED here, it will be equals to 1000 for the maximum punching shear. And then the K, it will be the same as what we calculated earlier on when we calculate the punching shear at 2D perimeter. It is basically referring to this table here. We need to get the ratio between C1 per C2. C1 is 300, C2 is 150. That gives you C1 per C2 ratio equals to 2.0. Then you know that your K will be equals to 0.7. Substitute the value into the equation, you get your beta equals to 2.05. And then you can get your shear stress, which is equals to 4.67. You will do the same for the minor axis. However, in this case, your moment it will be equals to 0. 0 moment here will lead to this whole thing equals to 0, and your beta will be equals to 1.0. Therefore, it is no point for you to calculate the W1 in the minor axis. Take the beta equals to 1. Substitute the VED, which is 1000, U0, which is 900, and the effective depth, which is the average effective depth of the major and the minor axis, giving you the D equals to 488 mm. You get your shear stress equals to 2.28. What you see here, since there will be moment in the major axis, the shear stress it will be more critical in the major axis. In fact, if you wish to simplify your calculation steps, normally you will check the maximum punching shear in the directions of the moment. Now, if you are not confident, you can always check for both sides. And then check against the VRD max. This is the formula for the VRD max. However, you don't see this formula in Eurocode. This is a derived formula from Eurocode, where the derivations process is demonstrated here. For simplicity, we just use this formula. To calculate VRD max, you need FCK. FCK in this case is equals to 30 Newton per mm square. And then you have partial factor of safety of concrete, which is equals to 1.5. And also alpha CC, the factor is equals to 1.0. Based on the formula, you get VRD max equals to 5.28 Newton per mm square. Compare the resistance with the shear stress. the resistance is greater than the shear stress, then you know that the maximum shear resistance is adequate. In the case that it is inadequate, you will need to increase the thickness of the peg footing that you proposed. Having the thickness of the peg footing increase, your effective depth shall increase. Having the effective depth increased, now you will have a greater effective shear areas taking the shear force. This will result in lower shear stress, and you will have to test the appropriate thickness of the peg footing until you come to a state that the shear resistance is greater than the shear stress. Now that we have covered all three shear resistance, although they are all shear, but individually they represent different situations. We have the shear resistance at the shear plane located at 1D from the column face. We have also punching shear resistance at the shear plane located at the perimeter of 2D from the column face. And also we have the maximum punching shear at the perimeter, same as the column perimeter. Not only the shear planes happen at different locations, the equation used to determine the shear resistance for each of them differs. The shear resistance at 1D will depend on VRDC and VRDC mean. Whereas if you're talking about the punching shear at 2D, we use VRDC mean divided by the effective shear areas at the parameters of 2D. As for the maximum punching shear, this maximum VRD is calculated. Therefore, you will need to be careful not to be confused with the shear resistance under each circumstances. Once you have done checking the shear resistance, you're going to check for other serviceability requirement, particularly in terms of the cracking resistance. First, you check the thickness of the peg footing. The proposed thickness is 550 mm. It is greater than 200 mm. That means you need to provide some mechanism to control the crack, particularly at the surface of the peg footing. In order to control the crack, you may position the perimeter reinforcement surrounding the edge of the peg footing, and the spacing between this reinforcement shall not be greater than 200 mm. Also, you're going to check for the maximum bar spacing. This can be determined from Table 7.3 and Eurocode 2 Part 1. You may use these formulas for you to determine the shear stress in the reinforcement, and then determine the maximum bar spacing based on the crack width of 0.3 mm. If you look at the equation here, you need information regarding the GK and QK. In order to quantify the ratio between the quasi-permanent load against the ultimate limit state. However, in this case, only ultimate loads are given, and the GK and QK are not given. We have no idea about the quantities of GKs and the QK. Not knowing what is GK and what is QK, we are unable to generate this number. Therefore, in this case, we will assume the ratio is equals to 0.6, assuming the quasi-permanent load is about 60% of the ultimate limit state load. Having this ratio multiply the FYK divided by partial factor of safety of the steel, which is 1.15. That gives you this part of the equation. You may also incorporate the influence of the reinforcement provided by taking the ratio of the AS required versus the AS provided. This you may refer to your calculation steps to determine the amount of reinforcement bar required to withstand the moment acting onto the peg footing. We have AS required for the major and the minor axis, and also AS provided in the major and the minor axis. Take the AS required divided by AS provided. You find your stress in the reinforcement, which is equals to 236 in the major axis and 198 in the minor axis. And then you may refer to the table 7.3n and do some interpolations based on the steel stresses. The calculated maximum spacing is 205 and 253 mm. We use the smaller value as the maximum bar spacing. And this maximum bar spacing shall be applied in both axes. Next, we will need to calculate the actual bar spacing based on the amount of reinforcement bar provided. You can sketch the arrangement of the reinforcement bar for you to determine the bar spacing. You may use these formulas for you to calculate the bar spacing for the major and the minor axis. If you find difficulty to understand this formula, you can imagine like this. Use the width of the peg footing minus 2 side concrete cover minus half size of the bar, half size of the bar, and the length left over shall be divided by total numbers of the reinforcement minus 1. The bar spacings that we are calculating is the center to center distance between two reinforcement bars. And why do we need to have this n-1? It is because the total number of the bar here equals to n will have n-1 units of spacing. From there, you obtain the bar spacing close to 150 mm. You will need to check this actual bar spacing against the maximum bar spacing. The bar spacing is less than the maximum bar spacing. That means the crack on the surface of the peg footing can be effectively controlled. In the design of the peg footing, you will need to ensure all aspects of the peg footing meets the requirement. This includes the surface soil pressure not exceeding the soil bearing capacity, the provided amount of reinforcement bar not less than the AS required calculated, the AS provided fall within the maximum and minimum bar area, the shear resistance at 1D from the column face is greater than the shear loads, the punching shear at parameter of 2D from column face not greater than the punching shear resistance. Also, the maximum punching shear at the column parameter not exceeding the maximum shear capacity, and also the cracking has been effectively controlled. Having all this done, you can conclude the final dimensions and the reinforcement bars. The final dimensions of the peg footing is 2.4 meters length times 2.2 meter width times 0.55 meter thickness. The main reinforcement bar is 15 units H12 at the spacing of 149 mm. And the secondary reinforcement, it will be 16 unit H12 at 153 mm. Also, don't forget about the arrangement of the reinforcement for a rectangular section. The proposed amount of reinforcement bar in the shorter directions shall have 2/3 of the reinforcement concentrated within the bandwidth of C plus 3D. The meaning of C plus 3D is the width of the column plus 1.5D at both sides. The D in this case, in the minor axis, it will be 4 at 2 mm. 1.5D is equals to 723. You have 300 plus 723 plus 723. That gives you these regions where you need to have 2/3 of the reinforcement, and the width here, it will be equals to 1.746 mm. Make sure you have at least 2/3 of the reinforcement concentrated at these regions for the secondary reinforcement. The reason being that you need to have this considered is due to the greater transverse moment near the column when the peg footing is subjected to the axial load. Having all this considered, now you can produce a safe reinforced concrete peg footing, which in this case resisting the axial load and the moment in the major axis.